Hello. So right now I am recording something just small for chemistry to finish the lesson that we've already done. Um, the tentative plan is that once it's like maybe February 1st, I won't just write subplans, but I will try to do a Google Meet or something so I can actively talk during the class, whatever it is we're doing, or if we're doing a lab, I'm quote unquote there in the Google Meet or whatever while you have the sub. But I'm just going to record myself to finish off this lesson on entropy. So you should have done the entropy reading and gone over the answers already. And so let's look at the definition. Entropy. Sometimes people define entropy as a measure of disorder or favoring mixing. These aren't really wrong, but aren't the most technically correct either. It's kind of like some other examples I've given in the past, where we can have like a surface level and then we can go deeper. And so here, yes, it is disorder mixing. It's not really wrong, but we can be a little more specific in what really entropy is, and sometimes that's necessary to understand what's going on. So here's a more technical definition. Each specific way, each arrangement of the energy of each molecule in the whole system at one instant is called a microstate. Entropy is measured by the number of accessible microstates. Now, the reading you use, or you just read, used the word arrangement. So you can think about it as the number of microstates or the number of possible arrangements. In other words, how many various uh, places or arrangements of the energy and positions of the particles could there be? And if there's more possible microstates or more possible arrangements, that means more entropy. Because if there's more arrangements, then there's a higher likelihood of it happening. So entropy, more possible microstates means more entropy. There is a different microstate when any particle has a different physical position or a different amount of energy. So if any of the particles are somewhere different or they have a different amount of energy than they had before, that's a different arrangement. And so the number of possible arrangements gets really big really quickly. You can think of just about when there were the sheep in the different fields, you increase the number of fields and sheep, and the number of possible arrangements of the sheep goes up really, really fast, right? These are some cases where entropy generally increases. Liquids generally are higher entropy than gas. Than solids, and then gas is higher than liquids. So you could pause this video and do a little bit of an outside analogy. Um, like I said, if it's in February, God willing, I will like actually be like, if I am going over notes or something like in the class where I'm physically kind of can pause it or whatever, it's not hopefully going to be like this because this is recordings is difficult, right? That'd be hard for a long time. But you could do an outside analogy where all of you act as if you're a solid. And so then you should get in a grid, kind of like when we do the ionic bonding, where everyone's equally spread apart. And you could be like about this far apart. Kind of, you don't have to be touching hands, but well, yeah, like you should be like this, but in a grid, as we've done sometimes, and then your hands can be touching each other. So that would be solid. Then for a liquid, keep your hands where they are and stay the same distance from everyone around you, but be moving around each other. That represents how in a liquid, the molecules or atoms aren't really that significantly more further away from each other than they are in a solid usually, maybe 4%, something like that, but they're moving around each other. Okay. Then for a gas, when it's time to become a gas, if you do this outside analogy, then all of you move randomly out in the field for 10 seconds to represent a gas. Well, all the particles aren't next to each other anymore. They're moving about randomly. And so if we were to diagram this, maybe it looks something like this, where here we have a solid, here we have a liquid with the particles moving around each other, and then gas, they're really far away, okay, and moving randomly. So we can see that if you go to liquids, there's more possible arrangements than there are for solids, because there's more positions that things can be, because they're freely moving around each other. Whereas gases, there's so many possibilities, because they're taking up so much space, and they could be all over an empty space, and any different arrangement is a different arrangement. Any different position of any of the particles is a different arrangement. Okay, other examples of entropy besides solids, liquids, and gases. If something splits into more parts, so if a chemical reaction has more products than reactants, meaning that there's like physically more products or more like the number of coefficients on the product side is greater than the number of coefficients on the reactant side. So for example, if we have A makes 2B plus C, this, and they're all, let's say they're all aqueous, or let's say they're all gas, okay? Well, here we have more entropy on the right because there's more products than there are reactants. So there's more molecules separated from each other. So that means there's, or atoms or whatever it is, so there's more possible positions they can take as opposed to having less like chemicals on the reactant side of the equation. Formation of a solution will also increase entropy. So for example, if we have NaCl solid, and as we've learned, you can pause this video and write it on the right-hand side. You can pause this video here again, take 30 seconds to write down what this will look like in dissolution. Okay, hopefully you pause the video and are able to do that. It could be something like this, Na plus Cl minus, and these are both aqueous. That is also increasing entropy, because now instead of a solid NaCl, now they are in solution and they're freely moving around in the water. If you remember that video we saw before of how water interacts and takes the ions from the salt and moves them all around in the water. Now there's many more possible arrangements of those salt atoms, so that's increasing entropy. Or temperature increases. If the temperature increases, the particles are moving more, so there's like more positions, you can think of it that way, and also there's more energy. And so the more energy you have, the more ways the energy can be shared among the particles. And so this is what you'll learn in the Boltzmann-Bucks game, where the Boltzmann-Bucks represent energy. And so the more energy there is, or the higher the temperature, the more possible distributions of energy there are. Right? If there's 20 of us and we only have $1, then there's 20 possible arrangements where it could be a different person with that $1. But if there's a lot of dollars, then there's more possible arrangements of those dollars. Okay, so these are the reasons why. And I said these, but here it is in writing, so you can see them again. So solids to liquids to gases. Why is entropy increasing? The particles are moving more, have more possible positions, called microstates, available, increasing entropy. Something splits into more parts, more products than reactants. Again, why? More total chemicals means more possible microstates. In other words, more total positions and more possible distributions of energy among them. Next, something splits into more parts. Formation of a solution. Why? With ions separated in solution, as opposed to a solid, there are more possible microstates, more total positions, and more possible distributions of energy among them. Temperature increases. Why? More possible microstates, as more possible distributions of energy, since there's more energy to be distributed. At this point, you should pause this video, and you should do the Boltzmann-Bucks game, where you will spread your money, and maybe someone will become rich, and maybe some other people will become poor, kind of like the real world. But it's the Boltzmann-Bucks game, entropy example. So then hopefully you've done the Boltzmann-Bucks game. And so you've gone over and you should have gone over the answers before you see the end of this. Okay, so what you did in the Boltzmann-Bucks game shows you close to a Boltzmann distribution, which is shown here. For any given particle at any given temperature, the range of possible energies that the particles can have is the Boltzmann distribution. Notice that there's some average, or there's a, can I say, a most common um, amount of energy the particles have. But you can see, so here we have the velocity of the particles. So this could be like a gas and the velocity of how fast the particles of the gas are moving. That would represent how much energy they have. You can see some have really high energy, some have really low. And this is the distribution, where there's some most common, but then there's some with less than that and some with more. That's the Boltzmann distribution. So it's actually entropy is higher or highest with this specific distribution. In other words, the Boltzmann distribution is the most likely distribution. It's less likely that everyone ends up or with the same amount of money just by chance, and it's less likely that by chance that all particles end up with the same amount of energy. So the more energy of particles, the more possible microstates, and so the more entropy. And so this gives more possible microstates than everyone having exactly the same amount. That's actually very unlikely that everyone would end up with exactly the same amount, or that all the particles are going to end up with exactly the same amount of energy. Now, let's kind of rope this in here with the last slide. So, together, enthalpy and entropy determine whether the change in free energy is positive or negative. If it is negative, the reaction is spontaneous. So, we can put this together and we can say, and let's see if I can even, okay, I'd like you to pause this for a second, and let's tell the person next to you, um, let's tell the person next to you for the reaction to be favorable, the most favorable, will enthalpy be positive or negative? Positive or negative? And will entropy be positive or negative? For reaction to be more favorable, generally. Okay? And then is G, as a result, would G be positive or negative? Okay, so tell me, are those three going to be positive or negative? Give 3 minutes, talk with people next to you. Okay, hopefully you've gone 3 minutes and talked with the people next to you. And, since this is a recording, let's have some fun with this. So, if we're in Chem A, okay, so show me what the value for enthalpy should be. Well, either one, Chem A, Chem B. What's the value for enthalpy? Show me with a plus or negative which one it is. You should say that it is negative, right? A negative enthalpy. What is enthalpy again? What is enthalpy again? If we're in Chem A, let's have Levi answer this. And if we're in Chem B, let's have Wesley. What's so just have some fun. Levi, Wesley, what is enthalpy? Okay, I'm sure you got it right. And if not, someone else helped you out. But I'm sure you didn't need any help. I can read the future here. You said it's the energy stored in the chemicals, right? Good job. And so if the chemicals are losing energy, releasing energy, enthalpy is, again, everyone, negative, right? And if the chemicals are losing energy, is attraction going up or down? Show me with your fingers. Attraction's going up, right? And again, what is entropy? What is entropy? Tell the person next to you what is entropy. Okay, good job. So if sometimes I get these classes confused, but let's try this one more time. Oh, hopefully I don't mess this up. If we're in Chem A, let's have Timothy answer this. Pretty sure Timothy's in Chem A. And then if we're in Chem B, let's go with Deft. So Timothy and Deft, what is entropy? Yeah, good. You should say it's a measure of disorder, the number of microstates. And for a reaction to be more likely to be favorable, should entropy be positive or negative? Everyone, should it be positive or negative? You should say it should be positive. And then overall, you can notice here, if enthalpy is negative and entropy is positive, we get a negative, a negative minus a positive. And subtracting a positive is a negative. So you get a negative plus a negative. And a negative plus a negative makes a negative. So here's the last thing to get away. If it is negative, is spontaneous. So if change in G is negative, then it's spontaneous. So we can measure something spontaneous based on the relative enthalpy changes and the relative entropy changes. So based on how much the enthalpy changes and how much the entropy changes are, we can determine if something is going to be favorable, and that would give a negative total. It would be a release of free energy. Okay? So that is this lesson. I think also at this point you could take a moment to, if you finished this and you have time, maybe 10 minutes to finish looking at the outline questions. And then if you have the 10 minutes to look at the outline question, then the class after this, I don't know if that would be Monday or Wednesday, depending on when you, or Friday, whenever you finish it. But the next class after taking 10 minutes to review the outline questions based on what the sub/TAs tell me is going on will be the quiz on this material. So hopefully this video worked okay. Again, like I said, God willing, February I can do some sort of quote unquote live thing. Uh, yeah, but this is just for now. So God bless you. Never stop learning.